All right, the next topic is equilibrium of a rigid body. Okay, back in chapter 3, we talked about equilibrium of a particle, where we were just concerned about the forces canceling out. Summation of forces in the x, summation of forces in the y, summation of forces in the z. Okay, they all had to cancel out so the particle wouldn't move. The difference with a rigid body is now we're dealing with something that's got 3 dimensions to it. It's still rigid, which means it's not going to bend or deform at all as we put stresses on it. But this thing, a rigid body, as opposed to a particle which can just move, a rigid body can move and rotate. So we are going to be introducing moment into our equilibrium equations here. Okay, that does mean we end up with summation of forces equals 0, which is the same as a particle. We also have summation of moments equal to 0. Okay, the nice thing about this, while we still have summation of forces, which we can split into summation of forces in the x equals 0, summation of forces in the y equals 0, and summation of forces in the z equals 0. We have the same 3 things for moment. Okay, we can take summation of moment in about the x, summation of moment about the y, summation of moment about the z. All have to equal 0 as well. Okay, in 2-dimensional problems, okay, as we're looking at our xy axis, okay, we're only talking about things that will rotate like this, rotate on the xy plane. Things that are rotating on the xy plane are rotating about the z-axis. Okay, so there's not going to be any moment about the y or about the x in a 2D problem. In a 3D problem, we are going to have all 6. Okay, and again, setting up our free body diagrams on these things becomes fairly important on these. But before we get into actual examples here, we need to talk a little bit about support reactions. Okay, when we have an object, a rigid body here that's being supported, there's a number of different things we can do here. So support reactions. Okay, these are the different sort of structures or supports we can use to support our object, our rigid body here. So examples here include cables, which you should be familiar with in terms of using tension to support an object, rollers, pin joints, bearings. There's a whole number of these things. Okay, the 3 most common ways here. Start with as simple as a roller. Okay, say we have a beam. Okay, we've got the ground here. And there's this roller, this bearing, the circular bearing underneath it here. It's going to support the beam. This is going to allow the beam to move side to side as it rolls. It's going to allow it to rotate as it rolls over the thing. All it's going to do is prevent, so no translational motion in the vertical direction. So in terms of the force that it exerts, this support is really just going to, so we call this point A, it's going to have a support force in the y direction only. Again, it doesn't prevent it from rotating, so there's moment allowed. There's nothing resisting any moment, any torque there. It allows it to move side to side. There's nothing resisting it going that way. All it does is keep it from falling by supporting it with the roller there. And the next simplest one is a pin joint. Same idea. We have a beam. We have the ground. Only this time, instead of a roller on these, we put a pin through our beam and mount it onto the ground here. Okay, so this is, think of it as a hinge sort of thing, or I'm trying to think of a better real life example here. But essentially, we've taken our beam, we've driven a pin or a nail through it, so we're holding it like this. It's allowed to rotate, but we're keeping it from moving up or down or side to side. Okay, so this prevents movement, so no translation. In horizontal or vertical directions. Get my handwriting a little better here. Horizontal or vertical directions. So in terms of what this looks like, in terms of forces, we'll have, again, if we call this point A, we're going to have A in the Y and A in the X. Again, we don't know which direction those could be. A could be pointing to the right, or Y could, AX could be pointing to the right, AY could be pointed down. Doesn't matter which way we draw them. If we've drawn them the wrong direction, the answers will just come out negative, and we'll know we need to turn our arrows around. Okay? But our pin joint will support it like that. Note that it does still allow rotation around the pin. The last one is kind of a oxymoron. It's called a fixed support or fixed joint. Okay, calling a joint fixed doesn't seem intuitive to most people, to a lot of people here, but again, a joint is any time two objects are connected here. It can be a fixed joint, again, if it just doesn't allow movement. So here we're going to have our beam, and in this case, instead of thinking about the ground, think about we've just mounted it right to the wall here. Okay, this has been fixed on there. The best way to think about this is you've just glued it on there with this magical glue that doesn't ever give. Okay, this prevents all translation or rotation. Okay, so essentially this thing, we're going to call this point A again. The support here allows it to, prevents it from moving vertically, prevents it from moving horizontally, and it also there's a support moment at A, i.e. keeps it from rotating. Okay, this is the most stringent of our supports in that it supports movement in the X, Y, and potentially Z. Again, it doesn't allow movement in third dimension, even though we're only drawing it 2D here. And it also prevents moment about that point. Okay, there are literally dozens of different types of supports, joints, things that will that could be used to support your beam. Those are in a reference table in our textbook. Okay, so oops. Okay, a list of very common support forces in 2 dimensions is table 5.1. Which is pages 202 to 203. And for 3D, table 5-2, which is page 238 to 239 in the textbook. Okay, the idea here is that no matter what support you see in your diagram or see in your problem statement, if it's something you're not familiar with, you're always able to go look at these tables. They have pictures of what they'd look like in a diagram. They have names. They list the forces that they list the support forces associated with each particular joint, with each particular type of support. So anytime you're unsure of how of how a particular support will act on your beam or on your structure, you can go look at these tables and it'll tell you exactly how you need to include those on your free body diagram. Okay, we'll move forward with an example. The first one I want to take a look at here. So we have a beam kind of shaped like an angle here. Okay, I'm going to draw this longer. Okay, so we're going to put a pin joint right here. We're going to have just a smooth support here. This is a pin. This is what's called a smooth support. Okay, smooth support works exactly like a roller. This thing is allowed to go side to side, allowed to slide back and forth here, allowed to rotate over it. It's not allowed to move, obviously, into it there. Okay, this is not to scale. We'll call it 30 degrees. All right, in terms of distances, this is going to be 0.75 meters from, I'm going to do the dimensions in a different color here. This is going to be 0.75 meters from there to there. We're going to have 1 meter from here to here, and 0.5 meters from that one to the end. Okay, the reason I divided that up is because we're going to have an applied load force acting right here that's 60 newtons. Okay, and the other thing we're going to have is at the end here, we're going to have an applied moment of 90 Newton meters. Okay, applied moment is something that's going to be new for a lot of you. This is not a complicated idea. Just like you can have with a particle, you can have something applying a force, or a rigid body, something applying a force, allowed to push it side to side or back and forth. An applied moment, instead of pushing or pulling it, it's taking it at this point and twisting it. Okay, so there's no particular axis affiliated with this. It's just an applied moment. It works. It's oftentimes called a couple moment because it has the same properties as a moment applied by a couple. Okay, if you think back to the beginning part of chapter 4 when we talked about couple moments, okay, it's two forces that produce zero net force but produce a net moment. Same idea here. It follows all the same rules. Okay, you can apply it here because it is a couple moment. You can move it around anywhere in the problem you'd like to put it. So you can put it anywhere in your free body diagram. It's just there's something grabbing this thing and twisting it with a force or with a torque or moment of 90 Newton meters. Okay, so we're here with this diagram. Now we've got one applied load here. We've got a 90 Newton meter here. We're not given a weight, so we're going to assume the weight is negligible in comparison to the other things. That is a general rule of thumb. If you're not given a mass or a weight of your object, you can assume it's negligible in comparison to the applied forces. So all we need now is to draw in our support forces. Okay? Well, at the pin joint, we know what that's going to look like. We're going to have this will be, label some points here. This will be point A. Let's stay consistent here. And this will be point B. Here, it's going to be a bad spot to put it. B is there. Okay, we don't need any other points. So at A, we're going to have a support force in the Y. This marker's just a support force in the Y. We're going to have a support force in the X. Okay. I always draw my support forces in the positive directions, positive X, positive Y. I do that because it makes it easier for me later on to know, all right, if it comes out negative in the X, then I know what's left. If it's negative in the Y, I know it's down. That way I don't have to keep track which way did I draw my arrows, everything else. I just draw my support forces in the positive direction and worry about it later. Okay, the smooth support, it's not going to support it at all parallel to the beam. What it's going to do is support it perpendicular. So we're going to have a force B here. Support force at B. Okay, that is going to be at a right angle with the beam. That will become useful. This angle, unfortunately, I drew it a little steeper than 30 degrees, but we'll be able to work with that. Okay, so now we have this big mess of a diagram, but really we've got 1, 2, 3, 4 forces and a moment. Okay, we have 4 equations we can work with. We have summation of forces in the x, summation of forces in the y, and summation of forces in the z, all equaling 0. Those are our forces. We also have summation of moment equals 0. And in 2D, again, we're taking moment about some central point here. A moment about whatever point makes sense. And we'll end up using that in a second. Okay, so this is nice. We have 4 equations. We only have 3 unknowns, so we should be able to work with this pretty easily. Okay, summation of forces in the x gives us that AX, this has nothing, this is a moment, not a force, minus, okay, FB, the x component of FB. All right, I'll draw my little triangle here. Now, unfortunately, because the scale is a little off, this is my 30-degree angle. Is that correct? So that's going to be 30 degrees with the horizontal, 30 degrees. Yes, this is my 30-degree angle here. So FBX is actually going to be FB times the sine of 30. Okay. This equals 0. Summation of forces in the y, we have a y minus 60 minus FB cosine 30. Okay. That equals 0. Summation of forces in the z, we don't have anything. Again, 2D problem, we don't include z. That was an oversight on my part. So we are just going to have summation of moment equals 0. Okay, summation of moment, we can take moment about any point in the whole problem. Okay? You may think, oh, we should take moment here because that's where that moment's applied. Really though, this is a couple moment. We can move it wherever we want and it doesn't change anything. In that case, it makes sense to take the moment about point A. The reason being, if we take the moment about point A, that means the moment arms for AX and AY are both 0. Those fall out of our equation. So that way we're only dealing with one unknown. Okay, so that becomes a lot easier here. So this becomes, well, I'll do the whole thing out here. AX times 0 plus AY times 0 plus 60, again clockwise, so that's minus 60 times 1 meter. This is a clockwise moment, so that's minus 90. I'm going to do this. I'm going to leave my units in here for the sake of completeness here. Newtons times 1 meter. Okay, so that's going to be 60 Newton meters. We have this, which is minus 90 Newton meters. We have one more term here. We have this FB, which is causing a counterclockwise. So that's plus FB. We don't have to worry about X and Y here because we have the perpendicular distance is just this 0.75 meters. Okay, and this equals 0. So at this point we have 3 equations and 3 unknowns. Our 3 unknowns are AX, AY, and FB. Okay, this equation has 2 unknowns in it. This one has 2. This one, because these drop out, only has 1 unknown in it. Okay, so I'm going to rewrite this so that we can work with it here. So 60 times. So we can actually solve it here. So we're going to have 0 equals minus 60 newtons times 1 meter. minus 90 Newton meters plus FB times 0.75 meters. Okay, so we'll take these. 60 times 1 is 60. That's negative 60 minus 90 is negative 150. Bring that over, we end up with positive 150 Newton meters is FB times 0.75 meters. Divide through FB 150 divided by 0.75. I'm going to have to use the calculator. Should be able to do this in my head. Oh no, it's 200. Okay. 200 newtons. And then double check my sanity here. Yep. Okay. So force at B is 200 newtons. So I'll put that up here. So we know that one. Okay, so we did that with summation of moments about point A. Okay. We can also take this down. So we've used one of our three equations. We still have the other two, but now we know FB. These become fairly straightforward. Continuing with summation of forces on the Y here, we have AY minus 60 minus 200 cosine 30 degrees equals 0. We solve this for AY. AY ends up equaling 233 newtons. Summation of forces of X, we have AX minus 200 sine 30 equals 0. That becomes AX equaling 100 newtons. Both of these are positive, meaning I did draw these in the correct direction. Okay, which means we're left with showing that to support this thing, this little smooth support here is pushing this way with 200 newtons, again to keep it from rotating. This support here is holding it up and keeping it, again it's pushing to the right, so it's keeping it from moving left. Okay, this thing's pushing this way, we need an equal force in the X direction pushing that way. So this resolves and tells us what the support forces are acting up on this beam, holding it in place. Okay, we have this beam supported by a smooth support, a pin joint with an applied force, an applied moment, and it resolved into this structure here with these three support forces. Okay. Continue with one more example in 2 dimensions, which shows one other thing I want to show. Continuing here, we have, next we'll take a look at, we're going to have a fixed wall here with a beam that is pinned at the end here. I may have drawing this a little bit too big, but that's fine. This is pinned here. We have a pin joint there and a pin joint there. So this is going to be, we have another beam here. This is a pin connecting the two beams together. So again, it supports it from moving side to side against each other and up and down, but it allows rotation. We have another pin joint right here holding that end of that. And hanging from here, do my force in a different color. Hanging from here, we have a weight that is 700 kilograms. $700-kilogram mass hanging from there. Dimensions here, this. Do this in green. 1.7 meters from there to there. We have 1 point. Okay, hold on. We're going to make that 1.5 meters. We'll make this 2 meters. This distance here will be 1.5 meters. And again, let's keep this, so it looks like something close to scale. We'll make this 3.5. Okay, so now we're gonna label some points here. We'll call this point A. It's there, we'll go B, C, and D. All right, so this gets a little tricky in that we had two beams to deal with. Both of them need free body diagrams, okay? What we're trying to find here is find the support forces we'll just do the support forces. At A and B. Okay? So we have free body diagram of this whole big setup. I'll just draw it a little smaller here. Free body diagram here. This is the basic outline of our structure. Okay, we have a force over here that is this will be my free body diagram. Okay, we have force over there, which is 700 times 9.8. Is 6860 newtons. Okay, we have forces acting at A. We have AY and AX, and at B we have BY and BX. Okay, so that's going to leave us with 4 unknowns. All right, we'll see what we can do with this. Okay, so we've got summation of forces. I'm going to take this piece down. Summation of forces in the x equals 0, summation of forces in the y equals 0, and summation of moment equals 0. Again, still only working in 2 dimensions. Okay, we can do a couple of different things here though that it's going to allow us to work with this. Okay, so summation of forces in the x is just going to tell us that ax plus bx equals 0. Summation of forces in the y is going to tell me that AY plus BY minus 6860 is equal to 0. Summation of moment, okay, it makes sense to take moment about B, where we're going to drop a couple things out, or about A, where we're going to be able to drop a couple things out. All right? So as it turns out, this is going to be we're not going to be able to complete this right entirely today, but we're going to get far enough along that we'll be able to see what we can do with it later. Okay, so we have summation of moment. We'll take moment about A. That seems to make the most sense. So I'll take moment about A. That gives me summation of moment about A. That means both of the AX and AY have no moment on them. That also means BY has no moment on them. Okay, so that means we're left with with BX and the 6860 applied force. So the 6860 works clockwise, so that's going to be minus 6860 times its moment arm is this length, which is 3.5 meters. Okay. We have BX, which is causing rotation as we've drawn it counterclockwise, so that's positive. BX times its moment arm is from A to B here is 2 meters. That equals 0. Okay, so we're left with, working with here, we have summation of forces, so we have 6860 times 3.5 is 24,010 plus 2bx equals 0. Rearrange, that gives me bx equals, that divided by 2 is going to be 12.05 newtons. Okay, so 12,005 newtons in the positive direction, which makes sense. If we think about this thing, this thing is going to try and torque it downward. Bx here has to push back to support it that way. Okay, what this is also going to tell us is summation of forces in the x. This now becomes ax plus 12,005 equals 0. So ax has to equal negative 12,005 newtons. Okay. So what we're left with here is ax is actually pulling in the opposite direction from what we drew it. So this force is actually trying to twist it this way. These forces are actually working this way. Again, this actually turns into a couple here. Turns the other way to try and torque it back counterclockwise to hold this thing up. What we haven't been able to do is resolve anything in the y. Okay, this is going to lead me to a couple things later on. One is to be able to separate these two and do the free body diagram separately, where we have a support force at C. That comes along in chapter 6. Okay, we also have special properties of beam BC, which I'm going to talk about here in a second, which would have allowed us to solve the problem. But for now, this is what's called a problem with redundant constraints. I'll talk about that at the end of this lecture, talking about statically determinate structures and when they are and when they're not. But as we've taken it right now, we've got more constraints, more unknowns, 1, 2, 3, 4, than we have equations of equilibrium. So we don't have enough to solve it. Okay, there is one other little rule here that is going to allow us to do that, and that's going to lead us into that. So we'll go with that. So taking a look at in particular, well, leading into the topic here, is two force members. Okay, this is the case when we're looking at any beam, piece, member of a structure that has, let's draw a little beam here. Ooh, I'm going to try and draw something a little bit neater. Okay, if this thing only has two forces acting on it, okay, forces on any two-force member must be equal, opposite, and on the same line, and act on the same line. Okay, the reason for this, if I only have two forces acting on this beam, if they're not equal and opposite, okay, or if one of them's bigger, or if they're not exactly opposite to each other, this is going to cause this beam to move. Okay, in terms of forces, if the forces aren't equal and opposite, then there's going to be a non-zero net force. The thing is going to move, and we're going to have a non-zero, we're going to have a non-static problem. Okay, if they are equal and opposite, but not on the same line, okay, now we have equilibrium in terms of force, but we don't have equilibrium in terms of moment. If we have a setup like this, we're going to have this thing rotate. So we have to have, anytime there's two forces on a beam, if we have more than two, these rules go out the window because then they can balance each other out using the third force. But we have to have equal and opposite and on the same line. So it can look like this is the most typical case. Equal and opposite is going to pull apart, or equivalent the other way with compression, pushing in, and it's not going to cause anything to move at all. Again, assuming those forces are equal, it's not going to move left or right, it's certainly not going to move up or down, and it's not going to rotate. It doesn't have to be along the line of the beam though. If we have from corner to, I'll try and draw this as carefully as I can here. If I were to draw a line, geez. Fill in my beam here again. If I were to draw a line, it's good enough. Okay. Now, if I had one force going here and one force going here, those are equal and opposite and on the same line. Imagine that's a straight line. My art skills are a little lacking. Okay, so now we're pulling equal and opposite on the same line. Even though it's not parallel to the beam, it is still equal, opposite, and acting on the same line. This is really unusual, though. Typically, a two-force member is going to be nice and simple with either forces directly out or forces directly in. That would have allowed us to solve, if you think back to our last problem, when we had our structure that looked like this. Okay, we had A, B, C, and D. Beam BC was a two-force member. Okay, beam BC had to be a two-force member. Again, there's a force at B, a force at C, nothing else happening. Beam ACD, however, was not a two-force member. It had forces at A, forces at C, forces at D. Okay, and even though we split this into two components, it's still only one force. Okay, there's a force applied at B, a force applied at C. That would have allowed us to know that this force had to be along this line, which would have gotten us one step closer to solving it. Okay, but for now, I just want you to be familiar with two force members, because if you can spot those in a problem, it'll oftentimes save you a lot of time during the analysis. Okay, so two force members are going to give you a force that's equal and opposite and on the same line in order for that to work. The two-force member was a little bit of an aside there because it is a shortcut that can save you some time and effort, and sometimes get you a little closer to solving a problem that we're not quite ready to solve yet. But moving back to equilibrium of rigid bodies, I want to look at one 3D example. So if I were to take a look here, and this is going to tax my art skills a little bit. Okay, we have a beam that looks that's again. Okay. We have alright, so we have this pipe that's bent into this weird shape. Okay, for sanity's sake here, we'll just do all my axes. I'll make the origin, we'll put the origin here. It's Y, that's X, and that's Z. Okay, so this thing extends positive X, positive Y, positive X. It does not extend at all in the Z. We'll keep things simple for now. Okay, it's supported in three different places. we're going to have a support here. Support here. And a support. Where's the other one? Right in the middle? Nope, at the end. Okay, at the end here. All three of these supports are, and I'll start labeling points here. Call this point A, B, C. Are what's called journal bearings. Okay. Now, I'm assuming most of you aren't familiar with what a journal bearing is, and that's fine. That's why we go look at table 5.2 and figure out what the heck a journal bearing is. Okay. The picture in the diagram is much more clear than my artwork, I promise. But what a journal bearing is essentially you have the beam and you have basically a bearing that grabs it, or not grabs it, but almost like a hole here that allows it to slide back and forth, allows it to rotate, but what it doesn't do, it doesn't allow it to rotate around either of these axes. Okay, so if I'm looking at, so say we're looking at the journal bearing at point B. Okay, so our beam, I'm gonna do my marker thing here, our beam comes positive, X is out of the board Y's. We'll try to keep it straight here. So we have X, Y, and then X again. Okay, so I'm looking at my structure like this. I have a journal bearing holding this down here. Okay, holding it in place here. It's going to allow me to rotate around the Y-axis. Okay, the Y-axis is down this line. Okay, we're allowed to rotate around the Y. We aren't allowed to rotate around the X. That would be this way. Okay, the bearing's going to keep that from happening. And we're not allowed to rotate around the Z. That would be rotating this way. Again, the bearing is snug, so it's allowed to spin like this, but not back and forth or up and down. It will also allow it to move along the Y-axis, but not up in the Z, or not side to side in the X. Okay, so at A, support forces here. Okay, sometimes it's a lot easier to just make a list. At A we have, it's going to allow it to move in X, and it's going to allow it to rotate around X, but we have AY, AZ. We're going to have moment around the X and moment around the, we're going to have moment around Y and moment around Z. So at A, this thing is prevented from moving in the Y, prevented from moving in the Z. It's allowed to move in the X. So we have support in the Y, support in the Z, not in the X. In terms of rotation, it's not allowed to rotate around Y. It's not allowed to rotate around Z. It is allowed to rotate around X. So we have support in Y, support in Z, but not in X. Same rationale here at point C. So we're going to have CY, CZ, moment, I'll call this AY, moment around A at Z, moment around C at Y, and moment about C at Z. Okay. That brings us to B, because that one's tilted a little bit. This one allows movement in the Y, it allows rotation around the Y, so it's going to have BX and BZ, moment around BY, and moment around BZ. Sorry, X and Z. So at point A, we're allowed to move in X and rotate in X. At B, we're allowed to move in Y and rotate in Y. In C, we're allowed to move in X and rotate in X. So one thing I haven't told you is how the loading works on this. We have one force in the negative Z direction applied right here, and it's 450 newtons. Okay, we have some geometry here. We have dimensions, we're going to say this is 0.4 meters. This is 0.6 meters. And that middle piece is, again, not to scale here. This is 0.6 meters, and this is 0.6 meters. Okay, so B is halfway between the two bends in the beam, in the pipe. This is the length from A to the corner is 0.6, from C to the corner is 0.4. Okay, the question we're given with is find the support forces. Okay, this is an important distinction here. Okay, finding the support forces. Notice they did not ask us to find the support moments. This should be labeled as both, because it is both. And moments. Okay, so we have a total of 12 support forces and moments. But we're only looking for the support forces. So we're looking, so we can immediately just drop these. Okay, you're not often going to be looking for moments. If you're not asked to find support moments, assume you're not required to. Okay, so finding support forces. This allows us to work with just 6 unknowns, and the good news is we have 6 equations. So I will write down the unknowns here. So we'll have A, Y, A, Z, B, X, B, Z. These I'm just copying from over here to over here so I can use the board. C, Y, C, Z. Okay. I'm going to take this down. Alright. Now with this, it makes sense to go ahead and set up our equations for equilibrium here. So summation of forces in the X equals 0. Summation of forces in the Y equals 0. Summation of forces in the Z equals 0. I'll start with that. Okay, so in the X direction. In the X direction, we have no applied forces. Bx is the only one that has this, so we have Bx equals 0. That's beautiful. We're already eliminating one of our unknowns. Okay, summation of forces in the Y. This tells us, again, this doesn't give us anything in the Y, so we just have AY plus CY equals 0. Okay. And in the Z direction, we have a little bit more going on. All 3 of these support forces, all these act as forces in the Z. Okay, so we're going to go ahead and I'm going to say A, Z plus B, Z plus C, Z minus 450 equals 0. Okay, some of these forces may be directed downward. Again, we're assuming they're all acting upward for now. If they end up being downward, they'll just come out negative at the end. Okay, so now we have these 3 equations. We don't have much we can work with here. We still have the equations for moment, though, the ones we haven't used. Okay, even though we're not finding moments, we are still able to use the equations for moment. Okay, so what we're going to do here is take our summation of moments. I'll write these down. I'll write my force equations down here. So I'm going to have AY plus CY equals 0. And AZ plus BZ plus CZ minus 450 equals 0. Okay, so now we'll do summation of moments. Okay, summation of moments about the X. Okay, this part gets confusing, okay, because we're not dealing with moment in the problem. We don't have to use moment applied by any of the joints. We're just finding moments applied by these forces, okay? When I said, this is an important detail here, when I said B would prevent rotation, for instance B here, prevent rotation around the X or the Z, it's because of the forces, because of these forces keeping it in place that it does support that moment. Okay, so we're not going to apply an unknown moment here. These forces are going to be that moment. So, okay, so we have moment about the x-axis. Okay, we can take the moment about the actual x-axis or anywhere parallel to it, but it seems to make sense to take moment about the x-axis. Okay, I'm going to draw in my other forces here. B, we have a force at positive x. At C, we have a force, we're assuming positive y. And at A, we have a force also positive y. Okay. So, how many of these are going to cause rotation about the x-axis? These two forces are on the x-axis, don't cause rotation. Bx is parallel to the x-axis, won't cause rotation about the x. Bz will cause it to rotate this way. So, and if I construct my little marker beam here, okay, if I've got this is my beam here, if I have a support force of B pushing up here, it's going to cause it to rotate about x. Again, rotation about x is this direction. Okay, so forces at A aren't going to cause it to rotate at all. Bx would cause it to move this way. That's not rotation about the x, that's rotation about z. We'll get to that in a second. Okay, but Bx causes rotation this way, and we go to C. Cy pulls this way, that's not rotation about x. Cz, that's upward, that will be rotation about x. Okay, this is confusing. Okay, I know this is sometimes very tough to envision. If you have trouble with this, you can always go back to R cross F. That becomes very, very long in this case though, because all of a sudden now we have 1, 2, 3, 4, 5, 6, 7 forces, okay, all of them with their own moment arms, and you have to do R cross F for each. Okay, if you want to do that, it absolutely does work, but it is a little easier if you can start envisioning this thing. So Bz is going to cause a moment. Okay, so we have it's equal 0 is equal to Bz times this moment arm is 0.6. That is, again looking at that, that is going to be counterclockwise, so that's positive. This rotating about the x, we have 450, that's rotating this way. That is clockwise about the x, so that's plus 450. The moment arm from here to here, where the 450 applied, is 1.2, 0.6 plus 0.6. Cz is the other one that causes moment about the x. Okay, we have this beam that goes this way, causes rotation this way about the x. So we have a minus. Again, that's counterclockwise, so that's plus. This is minus. Plus. Again, Bz counterclockwise, the 450 clockwise, Cz counterclockwise. So that's plus Cz times, again, 0.6 plus 6 is 1.2. Okay. So this one we have two unknowns. Summation of moment about y. Same process. Okay, now we have a y-axis. These are, I didn't draw this, the origin is actually at A, so these don't cause any rotation. Okay, when we look at point B, Bz, okay, rotation about y is, dropping stuff here, rotation about y is rotation this way. Okay, I'm trying to, over here maybe a little better. Rotation about y is rotation here, okay? So parallel with B, I'm trying to hold this as carefully as I can. So this follows my beam. Rotation about y is going to be this rotation, okay? Swinging around this y-axis here. So moment about y, this does not cause any moment, there's no moment on it. Bx would cause rotation, again, this way, but not, again, Bx would cause rotation. I should have gotten something shaped like this object. But Bx is going to cause rotation this way. That's about the z-axis, it's not about the y. Bz will cause rotation about the y. That does count. The 450 cause rotation about the y. Cz will cause rotation about the y. Cy does not. So, moment about y here, we have Bz times distance from the y-axis is 0.6. Okay, looking at it from the positive y-axis, this is causing rotation in a clockwise direction. So that's negative. Minus 450. So, sorry, the 450 downward. Okay, this is actually causing, again, if you look at positive y, it's going to cause rotation this way. That's counterclockwise. So plus 450 times the distance here is 0.6. Cz, again, looking at from the positive y, Cz is going to cause rotation in the clockwise direction. So that's minus Cz times its distance is 0.6 plus 0.4 is 1. Okay, these two we could actually solve simultaneously and get Bz and Cz. But I'm going to hold off on that. I'm going to set up the equation for a moment about z first, and then we'll solve from there. Summation of moment about z equals 0. Moment about z. Now we're looking at this thing from the top. So we have my little structure here. Now we're looking at it from the top and having it rotate like this. Okay. So again, taking it from the top and having it rotate like this. Again, we're taking moment about A. These are all moments about A. You can choose any point you'd like. You get different equations depending on which point you take, but you should be able to solve them regardless. I could have chosen C and gotten a different set. I could have chosen B. You end up with slightly different moment arms, but the relationships end up being the same. So moment about Z. Because I'm taking the moment about A, those two drop again. Okay. Bz does not cause moment about the Z. It caused moment X and Y, but not about the Z. Bx is going to cause this thing to rotate about Z. So if I have my little here again, if I pull in this direction, it is going to cause it to rotate about Z. So we end up with Bz, and that looking from above is a clockwise rotation. So this is negative Bx times that distance from the z-axis is 0.6, is actually this distance, so it's going to be, nope, Bx distance from the z-axis is going to be 0.6, 0.6. That's a little annoying. So we're going to have that distance there, which is the square root of 0.6 squared plus 0.6 squared. Okay. Distance from the x-axis to where this force is applied is down this 0.6 and down this 0.6. Okay. We want perpendicular distance. What am I doing? I apologize. Perpendicular. This is acting along the x-axis. We want distance in the y. So that's just 0.6. That's this distance. Again, this distance is parallel with the force. It doesn't matter. I apologize for my mistake there. It is just this distance here. Okay, 450 is acting in the z. It's not going to cause rotation about the z. Cz acting in the z, not going to cause rotation about the z. Cy is going to cause rotation. Same idea here. We have our structure. We start pulling out. We start pulling outward on this end. Okay, it's going to cause rotation like this. That is rotation about the z. Again, looking from above, that is counterclockwise. So this is plus Cy times its perpendicular distance is 4, and 0.4 and 0.6 is 1. Okay, so now we still have 5 unknowns, but we also have 5 equations. Okay, 2 of these we can solve simultaneously. We have this one and this one, which we can work together. I'm going to move this one down a little bit and give me some space here. So I have moment about z is equal to 0 is equal to, what was that? That was minus bx times 0.6 plus cy times 1. Okay. So we have our commands, we have our equations here. We can solve these two simultaneously. I'll rewrite this one as CZ is equal to minus 0.6 BZ plus 450 times 0.6 is 270. That gets substituted in here. So we have 0 equals 0.6 BZ minus 450 times 1.2 plus CZ is now equal to this mess. So minus 0.6 BZ plus 270. Okay? And that gets multiplied by 1.2. From here, it's just an algebra problem. Okay, we solve this out. We have 0.6 BZ times 1.2. We'll take this out to the end here. So we have minus 450 times 1.2, 270 times 1.2. 16 divided by, so we have 0.6 minus 1.2 times 0.6 is negative 0.12. 2.6 is equal to, so BZ is going to be quite strong in the negative direction, but that's okay. Divided by is negative 1800 newtons. So BZ is a negative 1800 newtons. Okay, BZ. So now we can go ahead and plug that back in here. So this equals 0.6 times negative 1800 times plus 270. So CZ is going to equal 1350 positive 1350 newtons. Okay. So at this point we've used moment of the x, moment of the y, and that's given us BZ and CZ. I'm going to take these two equations down. That was the hardest part of the math. And we'll solve from there. Okay, so we still have AY, CY, and AZ. Okay, this uses AY and CY. This one we can get AZ out of, so we'll do that. And this one we can get CY out of. We'll use this one. Bring that up here. We have 0 equals minus, I should have done this right off the bat. BX is 0, so CY is 0. So we have minus 0 times 0.6 plus CY times 1. This goes to 0. CY times 1 equals 0. CY is 0. Okay, so there's no forces, and that's going to give us, for this equation, AY plus CY is 0. If CY is 0, AY has to be 0. That tells us that AY, BX, and CY are all 0. There's nothing happening causing this to rotate at all about the Z, move in the XY plane at all. Everything is happening in the Z direction. But there was no way to know that without doing, no way to know that for sure without doing the analysis. So at this point, we've used those. We've also used this one. We just need to find AZ. We have one equation left. AZ plus BZ is minus 1800 plus CZ is 1350 minus 450 equals 0. Okay, so we end up with, I'll do this on the calculator, make sure I get it right. So 1800 plus 450 is 2250. It should be 900, I believe. 1800 plus 450 minus 1350 is 900. AZ is a positive 900. Okay, and those are our support forces. If that seems tremendously long and drawn out, it's because it is. There's really no simple way to do a three-dimensional rigid body problem without ending up with 6 equations and 6 unknowns. I'll tell you, in this course, we'll never deal with anything where you have to solve more than 2 equations and 2 unknowns at a time. For instance, this one, we had to solve the 2 equations at once, solve them simultaneously by substitution. But from there, we were able to do just 1 equation at a time and fill in the rest of our unknowns. Okay, so these problems are about as ugly as it gets in this course. They do get very difficult, though, particularly with trying to envision which way things are rotating. It is a little easier when you're dealing with a better diagram than my hand-drawn thing there, but it does get us an answer, and it does tell us what all these support forces are. Okay. One last thing I need to talk about is not a computationally based thing. It's just kind of a theory and terminology issue, and that is static determinacy. So, which I will write. Okay, statical determinacy is essentially the term that describes whether or not a problem can be solved using the analysis you learn in statics, using a static-based analysis. There are a couple of things that can prevent this. One is improper constraints. Improper constraints are when you have a problem where the beam or the object, the support forces aren't enough to keep the beam from moving. You don't get equilibrium. So for instance, if I had a beam that looked, let's say I had 2 forces acting on it, one like this and one like this, there's no way that's an equilibrium. Okay? These are improper constraints. No matter what's going on, no matter what the value of these forces are, this beam is going to move. This object's going to move. It's no longer a statics problem, it's moving. It's now a dynamics problem. Okay, so improper constraints are when you don't have the right support forces or enough support forces to keep the object stationary. The other problem is what we ran into in the second example, where I had to hand wave at the y components of those support forces. And that's redundant constraints. Okay, that's redundant constraints. So when you're dealing with redundant constraints, that's when you have more unknowns. You have so many support forces, so many forces applied to your object, that you have more forces, more unknown forces than you have equations to work with. What that means is what we had in that problem in that second example, where we're not able to find out what those forces are simply because there's not enough information given in the problem or given in the scenario to resolve it. There are some things you can do involving strength of materials and measured loading there to try and determine how those loads get distributed, but for the purposes of this course, we're just going to say redundant constraints and say it's not a statics problem. I will say every problem I give you on any homework in class in an exam is always going to be a statically determinate problem. I'm not going to throw any trick questions at you where you spend a bunch of time trying to solve it just to find out that it's redundant or it's improper or whatever else. That example I did will be the only redundant constraint problem you'll see this entire course. You won't see any improper constraints. But you do need to be familiar with the phrase statically determinate and what sort of situations you can have a problem that's not statically determined. And that's it.